Hi guys, welcome to the tutorial of binary optical neural network simulator. This is a transaction level cycle through Python based simulator for evaluation of various optical accelerators on different binary neural network models. The installation and execution of this simulator is pretty straightforward. You can clone this repository using the command over here. I have cloned the repository and opened it in a IDE. Here I'm using Visual Studio Code. So the project structure looks like this, and the main configuration where the user can provide information about their accelerator is in main.py. As you can see, the accelerator has different configuration parameters. The information of these parameters is provided in readme.md5 here. As you can see, the first parameter, element size, corresponds to the dot product size that a processing unit of the accelerator. Second is element count, which is the number of parallel dot product operations supported by a single processing unit. Unit count determines the number of processing units present in the accelerator. Then there are several other parameters, and the information of them is provided here. So currently, some of the accelerator types which are supported are given over here, and users can add their own architectures by changing certain files which are mentioned over here. Then so after the user has defined his accelerator architecture, he can choose the models which he wants to run the evaluation on. So the simulator provides these predefined models which are already available, and if a user wishes to add more models, he just have to add the model over here, and the simulator can pick those models and perform evaluation on them. So for demo purpose, I'm using these three models. If you comment out this, then simulator will pick all the models in the CNN models directory and generate results for all of them. So after the results are generated, we can provide the path where you want to save the simulation results. Here I'm trying to simulate our aux bin at 50 Gbps rate. So I've named it accordingly. To run the simulator, we can just run it, and to start execution, and it will provide you logs such as which model it is processing, whether the accelerator configuration, what are the layers being processed. Then at the end, it will also give the area, total latency, FPS, FPS per watt, and FPS per watt per area results on the console. And once the execution is finished, it will create the file, the results folder. So the accelerator also has the capability to determine or define the required precision and the actual precision supported by the accelerator. If the required precision is greater than the supported precision, then the simulator uses bit slicing to perform simulations. As the simulations are going on, I can explain a bit about the project structure. So the controller consists of the main scheduler, which schedules the convolution operations onto the accelerator or the mapping part. So the data flow will also be implemented here. Then exception is nothing but some custom exceptions related to the simulator. The hardware contains all the classes corresponding to various components in an accelerator, and users can define their own components and add it to the accelerator. While so the users can add their custom accelerators by changing the code shown over here. Then the performance metrics, it consists of various evaluation metrics like FPS per watt, and FPS per watt per area, and this has some predefined types. And for example, we look at the energy calculations. You can look at have information regarding Robin. So similarly, if a user wants to add one more architecture, they can add it over here and provide it while specifying the accelerator type. By now, it should have completed the execution. Yes, so it has completed the execution, and in the results folder, it has created this file, and this file will contain different information like the model being executed, the accelerator architecture name which we have provided, the configuration of the accelerator, the hardware utilization, which is the number of microrings being used during the execution, total latency, which is in nanoseconds, FPS, frames per second, total dynamic energy in watts, and total static power in watts. Then the other metrics like FPS per watt, area, and FPS per area per watt. Sorry, FPS per watt per area. Then once the simulation files are available, we also have a um, script which can provide illustrations and comparisons. So for this purpose, I have example visualization test.csv, which has different accelerators and their uh, performance metrics for different models. The script can take the CSV file and generate a comparison bar plot and also provide some simulation analysis results. Let us run this and see. So it would generate a file like this figure where it has clean comparison of them, and in the console it generates uh, the simulation analytics where it compares the given accelerator, the best performing two accelerators compared to the other accelerators. So uh, I think I've come to the end to the demo. So I would like you to try the simulator, and please let me know if you find any issues or if you want some more features to the simulator. And I would also like you to start this simulator. Thank you.